Imagine finding two gloves, one left and one right, separated into two boxes. You send one box to a friend across the globe without looking inside. When your friend opens their box and finds a right glove, you instantly know that the remaining box contains the left glove. This seems obvious, right? But what if those gloves were connected in a strange way, defying our everyday intuition? This is the essence of quantum entanglement, one of the most bizarre and fascinating phenomena in the quantum world. Two particles, no matter how far apart, can be linked in a way that their fates are intertwined. Measuring the state of one particle instantly determines the state of the other, even if they're light years away. This spooky action at a distance, as Einstein famously called it, has puzzled physicists for decades. It challenges our fundamental understanding of space and time, suggesting a connection between particles that transcends distance. The story of quantum entanglement begins in the early 20th century with the development of quantum mechanics, a revolutionary theory that describes the behavior of matter at the atomic and subatomic levels. Pioneers like Niels Bohr and Werner Heisenberg laid the foundations for this new understanding of the universe. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen, EPR, published a paper questioning the completeness of quantum mechanics. They argued that entanglement led to spooky action at a distance, implying faster-than-light communication, which contradicted Einstein's own theory of relativity. Erwin Schrödinger, another titan of quantum physics, coined the term entanglement and explored its implications. He believed that entanglement was not just a peculiar feature of quantum mechanics, but its defining feature. Despite the skepticism of Einstein and others, the concept of entanglement gradually gained acceptance through experimental verification. The work of John Bell in the 1960s provided a testable framework to distinguish between the predictions of quantum mechanics and those of classical physics. To understand entanglement, we need to embrace the strange rules that govern the quantum realm. Unlike our familiar macroscopic world, where objects have definite properties like position and momentum, quantum particles exist in a haze of probability. Imagine a coin spinning in the air, neither heads nor tails, but a blurry combination of both. This is analogous to a quantum particle's state before measurement. The act of measurement forces the particle to choose a definite state, like the coin landing on heads or tails. Entanglement takes this a step further. Imagine two coins spinning in the air, their outcomes linked. If one coin lands on heads, the other instantly snaps to tails, even if they're miles apart. This connection, this instantaneous correlation, is at the heart of entanglement. It's important to note that entanglement does not violate the speed of light. While the correlation between entangled particles is instantaneous, no information is being transmitted faster than light. Creating entanglement is like choreographing a delicate dance between particles. One common method involves using a process called spontaneous parametric down-conversion. In this process, a high-energy photon is passed through a special crystal, splitting it into two lower-energy photons. These newly created photons are entangled, their properties linked in a way that defies classical explanation. They are like two dancers perfectly mirroring each other's moves, no matter how far apart they are on the stage. Another way to create entanglement is by manipulating atoms or ions within a controlled environment. By carefully controlling their interactions, scientists can coax these particles into entangled states. Section 5. The Bell Test, Proving the Impossible. For decades, the debate over entanglement raged on. John Bell, a physicist at CERN, developed a groundbreaking theorem in 1964. Bell's theorem showed that quantum mechanics predictions differed from local realism. Local realism assumes objects have definite properties and influences can't travel faster than light. The Bell test measured correlations between entangled particles. Experiments by John Clauser and Stuart Friedman confirmed quantum mechanics, violating Bell's inequalities. The Bell test suggests our everyday intuition about the world is incomplete. Section 6. Quantum entanglement and real-world applications. Quantum entanglement, once an esoteric concept, is now poised to revolutionize various fields. From ultra-powerful computers to unbreakable encryption, its applications are vast. One promising area is quantum computing. Quantum computers employ qubits. Qubits can represent 0, 1, or both simultaneously. Entanglement amplifies this power. Another exciting avenue is quantum cryptography. It offers unbreakable encryption keys. Using entangled particles, they can generate a shared key, alerting to any eavesdropping attempts. Section 7. Quantum computing, a new era of computation. Quantum computing, fueled by entanglement, promises to revolutionize fields such as medicine, materials science, and artificial intelligence. With their unparalleled processing power, quantum computers could tackle problems that are currently intractable for even the most powerful classical computers. Imagine simulating the complex interactions of molecules to design new drugs and therapies, optimizing logistical networks to improve efficiency, or developing advanced artificial intelligence algorithms that can analyze vast amounts of data with unprecedented speed and accuracy. While still in its early stages, quantum computing is rapidly advancing. Companies and research institutions worldwide are racing to build larger, more stable quantum computers, pushing the boundaries of what's possible. Section 8. Quantum cryptography. Unbreakable security? In an age of increasing cybersecurity threats, quantum cryptography offers a beacon of hope for secure communication. By exploiting the unique properties of entanglement, quantum cryptography ensures that any attempt to intercept or eavesdrop on a communication will be instantly detected. This is because measuring the state of an entangled particle inevitably disturbs its state. If an eavesdropper tries to intercept an entangled particle carrying a secret key, they will inevitably leave a trace, alerting the legitimate users to the breach. While quantum cryptography is not yet a mainstream technology, it is rapidly gaining traction. Governments and private companies are investing heavily in its development, recognizing its potential to safeguard sensitive data in the future. Section 9. Quantum teleportation. Fact or fiction? Quantum teleportation, often relegated to the realm of science fiction, is another mind-boggling application of entanglement. It involves transferring the quantum state of one particle to another, distant particle, without physically moving the particle itself. Imagine beaming yourself from one location to another, Star Trek style. While not quite as glamorous, quantum teleportation achieves something remarkably similar at the quantum level. It's important to note that quantum teleportation doesn't involve transferring matter itself, but rather the information that defines the quantum state of a particle. This information is carried by entangled particles, allowing the reconstruction of the original state at a distant location. While still in its experimental stages, quantum teleportation has been demonstrated over increasingly large distances. It holds the potential to revolutionize fields such as communication and quantum information processing. Section 10. The future of quantum entanglement. Quantum entanglement, once a perplexing paradox, is now recognized as a fundamental principle of the universe. Its implications are far-reaching, pushing the boundaries of our understanding of reality and paving the way for technological advancements that were once unimaginable. As we delve deeper into the quantum realm, we can expect even more astonishing discoveries and applications of entanglement. From unraveling the mysteries of the early universe to developing revolutionary technologies, the future of quantum entanglement is brimming with possibilities. The journey into the quantum world is an invitation to embrace the unknown, to challenge our preconceived notions, and to explore the universe's most profound secrets.